Okay, so last time we studied a 2D Laplace equation in a disk. So we had Laplace on f equals to 0, and we had some boundary conditions. Some boundary condition that u of 1 phi was some u0 of phi. So this was a unit disk with coordinates r and phi. So to solve and the Laplace operator in this case was written as this. We have found a sufficient number of normal modes for this Laplace operators so that we could describe any solution inside the unit disk. So these modes were r to the n e to plus minus I and phi, and we used them. But there were also other modes, r to minus n, e to plus minus I and phi, and they have not played any role yet. So we will think about this set a bit later. So. Let us first remind how the solution inside the unit disk looked like. So we had Fourier expansion of u0 of phi at the boundary. So u0 of phi was a sum of u0 n, its Fourier modes, e to I and phi, and is integer, and so it was on one hand. On the other hand, we knew that all these expressions are killed by Laplace operator. So Laplacian of Rn e to plus minus I and phi was 0. So we could say that specializing here r to the n, and comparing with this Fourier series, we can continue, we can upgrade this expansion to the full solution of our equation inside the unit disk and write a formula that u of phi equals to sum of u0 n r to the absolute value of n, so that it is always positive power of n. It doesn't have singularities at 0. e to I and phi. We have the solution. And we can also ask if there is any universal formula that gives directly of phi starting from u0. Like, can we find a green function that describes this? So it means that we would like to have this formula. Oh, sorry, u of r phi. We would like to have this formula written in this form. U of r phi is the integral over from 0 to 2 theta. Oh, sorry, from 0 to pi d theta over pi, maybe just d theta. Green function of r phi theta u0 of theta. We'd like to have a formula like this that works for any function. So are there any questions about this so far? No. Yeah. So let us try to get such kind of a formula. So to do this, we need to substitute for a mode of u0 as explicit integral representations. So maybe that's fine. So how should we express u0n in terms of u0 of phi? Right, it is so from 0 to 2 pi d theta over 2 pi. And what should we write here? Yes, but what will this expression give if you integrate it with that series? Will it give you 0n or something else? What is the integral from 0 to 2 pi? What is this? Hmm? But yes, but is it what we need? So so what should be written here? Yes. Thanks. Yes, like this. Uh, and now, if you want to get the green function, uh, so we already have the structure that our boundary condition appears in the argument of an integral. So to get this form, we need to move this integral outside and compute the sum inside to compute the green function. So It is the integral from 0 to 2 pi, d theta over 2 pi, sum over integers r to absolute value of n e to I n phi minus theta times u0 of theta. So comparing it with this formula, we can write what the green function is. So green function of r phi theta is this 1 over 2 pi, the sum r to absolute value of n e to I n phi minus theta. But we can and we should compute the sum. So let us do this. We have actually computed such kind of a sum before when we studied the delta function. So let us just repeat that computation. So to do this, we can split the sum into positive and negative parts. So one will be the first sum is for positive ends and 0. So sum from n equals to 0 to infinity r to the n e to I n phi minus theta. Plus another sum which takes care of negative ends, and we also change n to minus n. So there is this expression, and now we simply compute two geometric progressions. They are well defined because r is inside, because our point is inside the unit disk, so r is less than 1. So is this plus and since this sum starts from 1, we should also put this term in the numerator. Okay, now let us simplify this expression. So in the denominator we have terms that come from this product, and this is 1. Then we have a product of these two terms plus r squared. And we have two cross terms that combine into 2 cosine. So minus 2r cosine of pi minus theta. And what do we have in the numerator? Well, maybe let us write everything first and then cancel. Oh, sorry, I wrote this n, it was a mistake. this plus all these two terms will cancel, and the answer for the green function is this formula. So we see that if r goes to 1, this this green function goes to 0, unless we are close to the point when phi equals to theta. So let us look at this more carefully. Theta is different from phi. Then this green function is proportional to 1 minus r squared, and this goes to 0. But in the other case, when r goes to 0, theta literally equals to phi. What do we have? This green function is equal to 1 over 2 pi 1 minus r squared over 1 minus r squared. Right? Because cosine equals to 1. So it equals to 1 plus r over 2 pi 1 minus r. And it goes to infinity. So, of course, we need some extra computations, but it is clear that it looks like a delta-like sequence. So we can conclude, we can guess that it is actually delta, something like delta 1 minus r, 1 minus r of theta minus phi. But we know that it is true actually just from the definition of this green function, because we know that the solution to Laplace equation is given by this formula. So if you take in this formula r going to 1, then we should recover the boundary value of u. So therefore, this kernel should be equal to a delta function. Because u of 1 phi equals to u0. So, yeah, sorry, thank you. Yes, yes, yeah. So we have this formula that the solution of r phi equals to a integral of d theta over 2 pi 1 minus r squared 1 minus 2r sine of phi minus theta plus r squared u0 of theta. And we know that the limit on r goes to 1 of u of r phi is equal to u0 of theta. So this green function of 1 phi theta equals to delta function. well, delta 1 minus r, phi minus theta. Or we can also write that g of 1 phi theta is a delta function. In the sense that it can be thought as a limit of this delta-like sequence. So do you have any questions about this? Oh, and of course, if you have mm, mm, some a special boundary condition, for example, given by a finite combination of trigonometric functions, there is no need to use this general formula with the green function. You can simply take this solution, knowing that you have only a finite number of terms, and most of the problems will be adjusted in this way, so that you don't need to sum such kind of series. Mm. Okay. Let us think about these expressions and what they remind us. So you remember that originally when we had to study this equation, it was convenient to introduce new variables like x minus t and probably x plus t. So precise variables are not that important. And this equation was written as u psi t is 0. But what if we try to do the same with the Laplace equation? So originally we have uxx plus uyy equals to 0, and it differs from this equation by a sign in front of the second term. So it suggests that we need to multiply one of these variables by I. So we can introduce coordinates. We can introduce homomorphic and anti-homomorphic coordinates. That equals x plus iy, and z bar equals to x minus iy. And what will the corresponding derivative equal to? So I'm writing dx plus dy dz bar. So it's also denoted by simply d, and this is denoted by d bar, which is equal to d in z bar. Dx plus dy. Well, And the question to you: what coefficients should we write here, and here? Where? Here. No, because when we differentiate z in z, it should be 1, but it gives 0. So it's definitely minus I. This should kill the bar. And is there any overall coefficient?
So it's the convex conjugate, so x plus I, the partial bar.
No, the question is it a correct expression or do we need to add anything else? Yes, thanks. Yes, and here, yes, here we have a complex conjugate. So if you want to connect the two operators, then dx squared plus dy squared equals to 4 dd bar. And now let us look at this normal modes. So our equation tells that u z bar equals to 0. So if we start solving this equation, we can do absolutely the same thing. We can say that the derivative of u is a function of the bar only, in the sense that it is oh no, the derivative of u is function of z only, because the bar derivative is 0. So u0 of z bar is equal to a function of z. It is holomorphic, it does not depend on the bar, because the bar derivative is 0. And then the next step is to note that if the derivative of something, let us call it f0 of z, if the derivative of something is a function of z only, then this original function was the integral of this function, which we can denote some other function. We don't need to know, we don't need to stick to this notation of f0, but it can also contain any anti-holomorphic function because its derivative in z is 0. So we conclude that u of z bar equals to f of z plus g of z bar. So, and comparing to the wave equation, here we had u of psi and eta, and eta was f of psi plus g of eta. But since the problems we pose to both equations are different, their solutions are also different. So the solution to a boundary problem for Laplace equation is more complicated as the solution for the initial problem for the wave equation. Because here we could simply find f and g, express them explicitly in terms of initial conditions, and simply shift two functions. But here we need some non-trivial green function. So it's a different situation. And now let us ask if you see such a structure in this solution. So of course we do see it uh, because z written in polar coordinates is what? Oh, can you tell me the formula? Yes, thanks. And z bar is r e2 minus I5. So these modes are z to n's and z and z bar to power n. And those modes are negative powers of z. So far we can write this solution for r u of r and phi using z and z bar. So from n equals to 0 to infinity, z to the n plus 1 to infinity let us write z bar. So we have holomorphic and anti-holomorphic components in this expansion. Right. And let me actually write this series in a slightly different form. Let me write it like this. From n equals to 1 to infinity plus u0, 0. Uh, so based on this representation, or also on that representation, we can notice one important thing. That namely, what is the value of this u computed at point 0? So let me write it. So it will be a remark, important remark. So what does value of u at 0 equal to? Yes, thanks. Or in other words, it equals to the integral of to the average value of u0 on a circle. So it equals to integral from 0 to 2 pi d theta over 2 pi u0 of theta. Or it is the same as to write that, so since it's on the boundary value, we can write that it is the average of u itself computed at this unit circle. So it's integral from 0 to 2 pi d theta over 2 pi u of 1 theta d theta. Uh, so this is value at 0, and this is the average on a circle. So can I read this, or did you want to say something? Yeah, so this remark is the following, that if we have a harmonic function, in a sense, a function that is killed by a Laplace operator, then uh, 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 u, then its value at an arbitrary point equals to, let us denote this point P. And let us denote this contour and this circular contour C. So we have this equality that u at this point equals to average value on a contour. And this holds for any point, because we could turn any solution of the Laplace equation into this kind of boundary problem. Like originally, we are solving this as a boundary problem, that we have values on a circle given to us by someone. But we can start from any harmonic function and choose any point and choose arbitrary circular contour centered at this point. And we have this equality that the value inside equals to average value on a contour. And immediate corollary of this fact is that harmonic functions cannot have a maxima or a minima inside inside the domain. So uh, so let me formulate it like can achieve minimum or maximum only at the boundary. So it's kind of first corollary, because so the proof is trivial. Suppose that it is a maximum. then how is it possible? It should equal to the average on the circle, but if it is a maximum, then mm, then and if a circle is small enough around this point, so so that there are no other maxima, how can this value be bigger than a value on a circle when it equals to average? So mm, mm, yes, of course, constant function is also homomorphic. So mm, it's possible, of course, but can we call any point the maximum or not? Only, but constant functions are, of course, not forbidden by this argument. So the value equal to mm, yes, yes. So yeah. And so another core is and that uh, mm, so it's also kind of trivial. If you don't have boundaries, if you live on a compact manifold, then the only harmonic functions are constants. So on the only harmonic functions on a compact manifold are constants. So and this also works in higher dimensions. We would need to modify this proof a little bit, but there is still this maximum principle, and there is this equality also in higher dimensions. We'll probably not prove it in full generality, although it can be done using the green function. But we'll see this explicitly, like in this case, in also in 3 dimensions, because we'll have the same description in terms of normal modes. But this is true in arbitrary dimension. Mm. Uh, so and another important modification of the statement is that the same holds for homomorphic functions. So uh, so I can replace a harmonic with homomorphic. And this is kind of obvious because homomorphic functions are also harmonic, because if d bar of f is 0, then automatically uh, d bar of f is 0 as well. And in some sense, all all harmonic functions are at least locally either holomorphic or anti-holomorphic. So it is kind of almost the same. And this in fact is very important because it allows us to learn many new things about homomorphic functions. Because the typical proof in a conformal analysis, when we need to reconstruct some function from its analytical properties, is the following. We try to invent some other function that has the same singularity structure, probably the same zeros or whatever else we need. And then we compare this function with the function we are studying. And if their difference or their ratio is holomorphic and it is defined on the whole complex plane with good behavior at infinity, which is equivalent to homomorphicity on a compactification of this plane, then we know that this function is constant. And if we know what this constant is, then we can reconstruct this function. So and this allows us to compute infinite sums, infinite products, and so on, and simply looking at the analytic structure. So it is very practically useful. And we'll actually see how this works in some similar in some simple cases. So let me. Okay, what can I raise? Probably probably I can raise on this. So we have this. So are there any questions about this? Yes. So we have already used the first set of normal modes, but we also have this negative powers. And natural guess is that they should be applicable to the external part of a circle of the disk. So let us look. Let us see what we already have. So we have r to minus absolute value of n to e to I n phi that correspond to that equal to z to minus n and z bar to minus n, and later equals in 0. But the question is it everything, is it all that we have in that domain or not? because this was obtained for n different from 0. But what happens if n equals to 0? So first of all, we have an angular part of the Laplace operator. So what are the solutions of this equation? So it was the eigenvalue equation. So I asked it to be minus n squared times f, and then put minus n squared equal to 0. So what are the possible solutions of this f? Hmm? Yes. Uh, of course, there is a problem with such a function because it's not single valued. But in principle, we can find problems with non-single valued solution. So if we need this, we can add such a function. Uh, and since this corresponds to n equals to 0, one option is not to have any power of r in front of it. So we can say that it is just phi. And the question is, can we express this function in terms of z and z bar? So what is phi in terms of z and z bar? Yes, yes. So it is b over 2i logarithm of z over z bar. So in principle, we have such a function. But we will not use it, just to know that it exists. So, then the question is more practical. So, namely, what happens from the radial part? So for the radial part, we have an equation RdR f, RdR squared f equals to 0. So let me call this phi. This. So what are possible solutions of this equation? Just a function of a single variable. How to solve this ODE? No. What happens if you act with this operator on R? R, dr, acting on 1 over R, on 1 over R equals to what? It differentiates R. Yes. And if you act once again, then it squares, of course. It will be minus 1 to the n, 1 over R. So it multiplies, this is a degree operator. It multiplies any power of R by this power. So this is degree operator, this is square of degree operator. So naively, what we would expect is some kind of R to power 0. But since this operator acts twice, there is some upgrade to this function of 0 degree.
It's like a constant plus a logarithm.
Yes, yes, precisely. Thanks.
What is the name of the operator?
A degree operator or dilatation operator, because if you compute the exponential of this operator, it will multiply r to the n by the corresponding exponential. Or if you, so you can write something like this: e to lambda, maybe better to write lambda to r d in dr, acting on r to the n will equal to lambda to the n, r to the n. So if extend it to all functions, we can say that lambda to r dr f of r is f of lambda r. So this is dilatation. And this can be called infinitesimal dilatation. Yeah, so this radial function is a plus b log of r. So and the point is that this solution is important because do you remember the formula for a gain function of Laplace operator in arbitrary dimension up to the overall factor? Hmm? Yes, and this is what we see here, and in arbitrary dimension it is 1 over r to n minus 2. So, so n equals 2 is exceptional, also because this function does not decay at infinity, unlike so. There's also an n equals 1 case when we have an absolute value of r. It was simply a double integral that recovers a function from its second derivative. So this is what we obtained now. maybe I can simply write, well, let it be R. Logarithm of R n equals 3 is 1 over R, n equals 4, 1 over R squared, and so on. With some coefficients. Here this coefficient is 1/2. Oh, maybe let me write those coefficients. On this, here we have 1 over 4 pi. And this coefficient should be found, because what we obtained here is a solution of our Laplace equation that is valid everywhere except 0. So it is precisely a problem that is needed when we want to compute the gain function. So we have this solution. Well, maybe, yeah, can still use this blackboard. So we have this situation when there is point 0, and there is a solution of Laplace equation defined everywhere else. So here we have this combination a plus b log of r. So we get that there might be some delta function sitting at 0, and we need to find which precise delta function is there. So we want to compute on the right-hand side of this equation. It is something times delta of r. So, and this coefficient should be found. So let us do this. In principle, we could obtain this coefficient from that computational gain function from the Fourier transform. We could take that limit carefully, but this is an illustration of another approach to such problems, that we can literally solve our equation everywhere except 0, and then just this solution to reproduce gain function with coefficient 1. So it's a demonstration of this demonstration of the advantage of generalized functions, because if you solve some equation with delta function on the right hand side, we can use all the methods to solve an equation without a right hand side everywhere except a single point. Yes, so and the trick here is very similar to what we did in one dimension. We can simply take this equation and integrate over a small disk around 0. So let us denote this disk D and integrate this. Let me denote this by C. Not write this sharp everywhere. So integral over D of the Laplacian of a plus b log r d2 r is so it is just c, because it is c times integral of a delta function. This is two-dimensional delta function in the sense that it is 0 everywhere except one point of a plane, and if we integrate it within the standard measure, it gives 1. So So then this integral can be written using Stokes' theorem. So it can be written as the integral of gradient over the boundary of this d. Gradient of a plus b log r. Yeah, dn is already here. But what does the gradient of this function equal to?
Since it's a real function, surely the gradient point in the direction of the end.
Yes.
Remember the name about
But you can compute it. Like, so what could the length be? I can remind you a formula for gradient for some function of. Yes, because it is er times dr f plus 1 over plus e phi 1 over r and phi f. It's kind of derivative in r phi, and this is derivative in r. Yeah, so b times er times 1 over r. And this is constant, so it doesn't contribute. So, and this dn equals to the absolute value of this vector equals to the length interval in the boundary, and is proportional to er. So we can write it as integral dl times er times b er 1 over r. But the length interval expressed in polar coordinates equals to what? It equals to d phi times r. So this is d phi times r times b over r, integral from 0 to 2 pi. So it equals to 2 pi times b. So if you want to find a green function, what should the formula for it be? Yes, thanks. Logarithm of the absolute value of r. But a in principle is defined up to a constant, so which we can remove if we don't like it. And such a behavior of this green function has also physical consequences because two-dimensional systems become much more correlated in this case. If you have something that is described uh, by the Laplace equation, then this field uh, will will have this long range correlations, but it also has mathematical consequences because, for example, let us try to formulate some a boundary value problem for this external part for unit disk and see what we need to fix in this problem to make its solution uniquely defined. Mm, so maybe I can erase this. So we would like to find a function like this. So there is a unit circle and we are so one, and we are studying external region. There is some boundary value u0 of phi. So we have a Laplace equation. We have a boundary value. And there should be some set infinity which we need to study now. Like so. Uh, let us study the simplest case. Let us try to ask this to be 0 and check whether it is possible. So if it was higher dimensional, like 3, then of course it would be possible. But let's see what happens in our case. So in our case, we have decaying modes equal to z to n and z to minus n and z bar to minus n. So suppose that this, well, let us try to write a solution of this equation using those modes. So u of z bar. So u0 of phi is given by its Fourier series. Okay, can you write a formula for u of r and phi uh, that has this boundary value for r equals to 1? Oh, well, what should we do here? Yes.
And I think we also need to have the fundamental solution to adjust some constants.
What do you mean by fundamental solution?
A constant norm because
No, it's a question. It should not necessarily go to zero. This is just a naive. Well, the actual boundary condition that can be satisfied with this, it should be of order 1. But, yes, so constant could be there, and it should actually be there. So. So what would you suggest to write here? We need to take this series and extend it to the whole external region by multiplying by some powers of r. So what should this powers of r be? Yes. But 0 is fine also. It is constant, so constant is fine. So and we see that this constant at infinity is actually is actually u0, 0. U of infinity phi is u0, 0. It's a bit similar to this maximum principle that the average value coincides with the limiting value. Yeah, so this is doable, but we see that since there is this requirement that it should be of order 1, we can in principle play with the asymptotics at infinity. Like, why should it be 1? Can we ask for some logarithmic asymptotics, for example? And maybe let me write this solution like this. Oh. let us study solution with non-trivial right-hand side. Right? Operation of u equals to rho. To rho of r. The question is, what can happen to this function at infinity? Well, the question is, can we ask that u of infinity is O of 1? Or should this synthetic be modified?
We are considering the problem on wall Rn or R2
Yes.
or
No, on the whole R2. So it's not a boundary problem. It is some problem with the right hand side. So to check this, and let us say that this rho is non-zero only inside some domain, like uh, let us ask it to have compact support. Uh, the point is that we cannot ask for such behavior because we can use the same argument as here, but for the equation with arbitrary right-hand side, we can integrate it over the big circle that contains a rho. So we can say that the integral of rho of r d to r, which we can call q, the total charge, equals to integral of Laplacian of u, Laplacian of u of r d to r equals to the integral over the boundary dn gradient of u, what equals to 2 pi over 2 pi times r times the integral of d5 over 2 pi gradient of u. So comparing this, we see that this average value of dr of u should equal to q over 2 pi r. Therefore, we see that this u at infinity should behave logarithmically. And the coefficient in front of this logarithm is equal to the total charge on the right hand side. So if you are solving some problem, some two-dimensional problem with some configuration of charges, and if those charges do not compensate each other, you will have this logarithmic asymptotics. So, so when r goes to infinity, u behaves like q over pi log r. And this is unavoidable.
But if we consider rho that has integral 0 over r2, then maybe we can find a solution.
Yes, of course. So if this configuration of charges compensates themselves, then it's fine. Yeah. So. Yeah, but actually, if you look at this asymptotics, we can invent another set of problems which includes non-trivial asymptotics at infinity. So we see that sometimes it is necessary to fix the asymptotics at infinity, and of course this asymptotics should solve our equation. So in principle, we can try to take some other solution and solve a problem like that, but with different asymptotics. And some of these problems have a clear physical meaning. So let us study one such example. So this is a problem about a metal sphere, which is a circle in this case. Or if it is, if we obtain this Laplace equation as a reduction from 3D by saying that that everything is constant along the third axis, then the circle can be interpreted as a cylinder. In the constant field. So we have a formula that electric field equals to minus a gradient of u. And we want this electric field at infinity to be constant. When r goes to infinity. So how can we write this constant field? Maybe is it better to ask? So suppose that this electric field is and in positive y direction. So have x and y, and the electric field E in this direction. What is the formula for U that would produce such an electric field? Let me write E goes to constant when R goes to infinity. Oh, what should we write there?
In what sense E tends to a constant, so
Mm.
pointing in the same direction as infinity?
Yes.
So it's already a
Mhm. So the problem is this. Suppose that E is just constant, like this. What should we write for U that would produce such a constant in the y direction? Yes, E times y, because it has non-trivial length. E times y, minus E times y, because there was negative sign. In principle, was some constant, but let us write this. Should not be a problem. Yeah, thanks. So, and how to write this in terms of r and phi?
y is r times sine phi, so
Mm-hmm. Yes, so it will be minus e r mm, or e to I phi minus e to minus I phi. Maybe we can just write sine. Mm, let's write sine. Mm. So, in this way, we have an idea about the asymptotics of U at infinity. So, if we want to formulate this boundary value problem, uh, we need to include this asymptotics there. So first of all, we of course have a Laplace equation. Then we should say that U of 1 and phi equals to 0. Uh, this is how metals or any other conductors behave. They have equal potential everywhere, because charges can freely move, and if there was some difference in the potential, they would move to that direction. So we can say that it is zero. We can say that it is some constant. Um, let us write that there is some constant C, or maybe tilde. So it's a boundary condition. We also have this asymptotics at infinity. R phi behaves like what we already found, minus E R sine of phi plus constant. And in principle, we could have there some coefficient like q over 2 pi logarithm of r. It's not prohibited because it is smaller than this r, but the interpretation of this coefficient is clearly the total charge of our metal sphere. So it is something that we can choose. So in principle, we can ask this coefficient to be 0, but not necessarily. A sphere of a circle. So and that's all what we can fix there. So now we need to solve this problem, right? Maybe let me just write this solution, or maybe you can try to guess on this. So you see that this function has a non-trivial phi dependence. So if we just take this naive expression and restrict it to r equals to 1, it will not satisfy this boundary condition. But do you have any idea how to write such kind of formula that it also satisfies the boundary condition? Can we add just one or two terms? Maybe just one term. Or maybe I don't even need this this blackboard. So the naive guess that we have all these terms literally written in the solution of our equation. But can we do something very simple to get rid of this term on the boundary? So it's solution. Do you have any idea? Like,
We have a gauge freedom, and we can choose to cancel it.
oh, but what do you mean by engage freedom? It is an electric field, like it's engaged invariant object. So if I restrict this term to the unit circle, it becomes E times sine phi. Do we have any term that behaves like this for r equals to 1, but decays at infinity? What if I just write this? Will it solve our equation? Because both r e to I phi and 1 over r e to I phi were solutions to, and also r e to minus I phi 1 over r e to minus I phi. They are all solutions. They are all harmonic. So if we specify uh, to 1, this u equals to just to c, because the logarithm of 1 is 0, and these two terms kill each other. So the picture is the following, that we have an external field and if you put this metal circle into this external field, we have a distribution of charges like this. So negative charges go to this part of the sphere, positive charges go to this part of the sphere. And it turns our metal sphere into this dipole. And this is called a dipole field. So let us remember this expression, and we'll probably see it next time. So, do you have any questions on this? Okay, thanks for your attention. See you next week. I'll add some extra problems in the next few days.